All right, today we're doing something a little different. We're going to take on a computer science exam. But listen, this isn't about just getting the right answers. It's about really understanding the core ideas that make our digital world tick. So let's just jump right in and crack this thing open.
So we're going to use the questions from this test as our guide. You can think of it like we're running a gauntlet together. And the goal isn't just to check a box, but to really get the why behind each problem. Trust me, by the time we're done, you'll see how these kinds of abstract questions are actually connected to pretty much everything you do online.
So here's our game plan for today. We're going to start by cracking some code. Then we'll move on to navigating data structures. After that, we'll tackle a classic algorithm, untangle a tricky networking concept, and then, at the very end, we'll pull it all together to see what we've really learned.
Okay, first up, let's get our hands dirty with a little C++ code. This first puzzle is all about a really powerful concept called references, and it shows you just how precise a computer has to be when it follows instructions.
So, let's take a look at question 2. It looks pretty simple, right? We've got two variables, x and y, and just a few lines of code. Our job is to play computer and figure out what their final values are after everything runs.
Go on, take a good look at it. You've got x starting at 10. But then there's this weird line, int and y equals x. What in the world does that little ampersand symbol do? Well, that little guy is the entire key to solving this puzzle.
Let's walk through this, line by line. That first line, int and y equals x, is creating something called a reference. The easiest way to think about it is that y just became a nickname for x. They're now pointing to the exact same spot in the computer's memory. So when the next line says y equals 25, it's not just changing y, it's changing that shared memory location, which means x is now also 25. They're linked. Then the code calculates a new value for x, 2 times 25, plus 30, which is 80. And here's the kicker, because y is just an alias for x. When x becomes 80, y becomes 82. So both x and y end up as 80, which means the answer is option 2.
Okay, so we've seen how a single line of code works. Now let's zoom out a bit to a much bigger picture. We're going to talk about data structures, and specifically something called a graph. You can just think of it as a bunch of dots connected by lines. Your social network? That's a graph. A map of the roads in your city? Yep, that's a graph too.
So, here in question 16, we've got a graph with all these nodes, S, A, B, C, and so on. Our mission is to visit these nodes in a very specific order. We're using a method called breadth first search, or BFS for short, and we have to start at node S. So how do we even begin?
First off, what even is breadth first search? Well, imagine you're standing at node S. BFS tells you to first visit all of your immediate neighbors before you go any further. Only after you visited all of them do you move on to their neighbors. It explores the graph level by level, like ripples in a pond. To keep track of who to visit next, it uses a queue. And a queue is simple. It's first in, first out, just like a line at the grocery store.
Okay, let's actually trace it out. We start at S, we visit it. Who are its neighbors? A, B, and C. So we add them to our queue in that order. Now we take the first person out of the line, A, we visit it. Next up is B, we visit that one. Then we get to C. Now, as we visit C, we look at its neighbors, which are D and E, and we add them to the back of our queue. Now the only ones left in line are D and E. So we visit D, then we visit E. And that's our path, S, A, B, C, D, E. That matches option 1 perfectly.
All right, so we went from a complex graph traversal, and now we're going to zoom way in on one of the most basic but most important data structures there is, the stack. It's super simple, but it's everywhere, from your browser's back button to how programs actually run.
Now, question 17 is a straight-up knowledge check. It's not a puzzle, but it's absolutely critical. It just asks, what is the basic behavior of a stack?
And the answer is last in, first out, or LIFO. The absolute best way to remember this is to just picture a stack of plates. When you wash a new plate, you put it on top of the stack, right? And when you need a plate, where do you take it from? The top! The last plate you put on is always the first one you take off. That's LIFO. It's the simple rule that powers the undo button in basically every program you use. This principle is the very definition of a stack, making option 3 our answer.
Okay, we've been focused on stuff happening inside one computer. Let's expand our view to the entire internet. We're going to untangle the conceptual models that make it possible for your computer to talk to a server halfway across the world.
So question 20 asks us to compare two different blueprints for how networks work. There's the theoretical 7-layer OSI model, and then there's the more practical TCP/IP model, which is what the internet actually uses. The question wants to know which layers from that big OSI model got sort of squished together in the TCP/IP model.
Here's the deal. The OSI model is super detailed, with 7 distinct layers. 2 of those are the session layer, which manages the conversation between computers, and the presentation layer, which handles data formatting. But the TCP/IP model is more streamlined. It's what people actually built. It takes all the jobs from the OSI's session, presentation, and application layers and just combines them into one single layer called the application layer. So the 2 layers that are missing, or rather absorbed, are the session and presentation layers. And that makes option 2 the right answer.
Phew. Okay, let's take a breath. We cracked some code, we navigated a graph, we mastered the stack, and we untangled the network. So what were the big ideas we just unlocked by doing all that?
Well, here are the big takeaways. First, we saw that code execution is incredibly precise and literal. One little symbol can change everything. Second, algorithms like BFS give us a logical, efficient way to explore huge, messy, interconnected data. Like finding the shortest route on a map. Third, really simple rules, like the stack's last in, first out principle, are the fundamental building blocks for really complex software. And finally, those networking models, they prove that using abstract layers is how we manage the immense complexity of global communication. Letting you watch this right now.
And here's the really cool part. These ideas, references, graphs, stacks, network layers, a lot of them are decades old. But they are the invisible engines running your social media feed, your online games, and your streaming movies this very second. Which really makes you wonder, right? What's the next big foundational idea being worked on in a lab somewhere today that's going to power all of our technology?